Hello everyone, this is a very short video that I'm going to record for you since I noticed that maybe some of you have problem with gradually varied flow. Gradually varied flow. So I solved the problem in module 5, the last session of module 5, which was module 5 EF second, I think what it was the name. And I have another example, review 2.1. These two examples are examples of gradually varied flow for water surface profile. How does it work when we say gradually varied flow? It means that for a length of the channel, water starts decreasing or increasing in level. And your job is to find it step by step. You had this one in your slides, and this tells you that you have two methods. First method says that you already have the distance and you want to see what is going on for that specific distance for y's. This is the examples from review second one. For the other method, which is implicit method, you don't have delta x, but you know what happens to y's. Your job is to find delta x. For this example, go to module 5. Let me double check the exact name for you. 5. Yeah. EF second, March 31st. But for today, I'm going to show you just how we did that. Before we start, we have this slide as a formula sheet for you. For both methods, you just need these slides. This could be written as Q2 over 2GA2. And you need this one as well for the first method, which is in module again 5EF2. You don't need to use it for the question that I solved last session. You need these ones for both of them and these ones for both of them. For critical flow, you have to use that. This one for rectangular, this one for the rest of cross sections. Okay, the first example was the one that I solved in March 31st. You had an example, you have Manning, you have the bed slope. Bed slope is here. Bed width is 3 meters. Side slopes are 1 to 1, so it's a trapezoidal. And you have the discharge of 19, and it says water surface profile until you got 5% greater than the depth, and you have Manning N. So this is the type of question that you don't have the length, but you have the two intervals. What are the intervals? One of them is the y that it mentioned, which happens here. The other one is this one. What is this? This is the depth 5% greater than uniform flow. What is this one? For sure, this happens as a control depth. What is control depth? YC or YN, depends on the control points. So to start with, you should use Manning and the original formula, which is this one, to find YC and YN. When you do that, you have the profile and you notice it should be M1. Why? Because your Y normal is more than YC. Being said, the possibility is valid in our program. So if you remember, you had a table like this. And as I mentioned, try to have as many as column that you can break down your calculation. We start with 4. Why? Here we go. The first steps is already given to you, so you don't need to go with the control point because you already have a specific point that question asks you. So I will keep the first point for. What about the last point? The last point says that yn, or normal depth, plus 5% of the normal depth. Your normal depth was 1.75. So 5% more than that, it's around this. So you should break down your calculation. How depends on the question. This one goes 0.1 meter for each intervals. In the exam, I will give you the intervals, or I will tell you how you will divide your steps. The rest of calculation is not that hard. Area by plus y2z, r area over p. And you can add even one more column for p to make sure that you have y plus v squared over 2g, or y plus q squared over 2g a squared. Delta E, keep that one blank. SF, you have the equation for SF. Here is that SF here. So use that one. SF bar, that's bar, keep that. You cannot calculate it here. S0 minus that, keep that, and put 0 for that. For the next one, do the same. When you find that, you can have S bar. S bar or SF average is the average of two data that you have. And for this one, use S0. What was your S0? 0.0015. So for this one, you just need to do 0.0015 minus the average. When you do that, for delta x, use this equation and find this one. You should continue it line by line until you get that one. What was the point? Again, you had two intervals, and if you remember, your profile was M1. So you had this one and this one. This one was 1.8, this one was 4. Your job was to find delta x. Your delta x is this number. Okay, the next one. The next one is something like that. You have this question at the end of the same module, 5EF2 March 1. Or another example is the one that I solved in review for you. So you have two examples of that. This one shows you when you have the intervals length, but you don't have the depths. Look at here, depths of flow, find it at 5, 25, and 10, 100 meter. So you have the length, you are looking for what happened to y. You have S, you have the information, you have Manning coefficient, you have discharge, and that's all you need. So what are you doing? You should start with YC again. YC, this equation. Why the easiest one? Because you have the rectangular channel. Keep that one. What about the YN? Use Manning for YN. When you use Manning, your YN is here. If I ask for the profile, compare these two, and you will notice that it's mild. If I ask 1, 2, or 3, you should be able to draw or sketch it for me based on if you have the Y. If not, you should predict that like the one here, concrete channels end in waterfall. So it means that at the waterfall, you have something like that. And you have a control point here. So you have YC here, YN here. For the last example that I solved, I gave you the Y. So you specifically have the Y. Here you just have two Ys, but you know that you are facing a waterfall. So back to the question. That's the M2, you have Y1, you have YC, and you know that at the end of a water, or let's say at the exact location of waterfall, you will experience YC. So you can say that the water goes down since it's YN, that's your YC, and clearly you can see that you have M2. That's a water profile. Now we will go for a table. For the table, look at here, the same table, but this time is a bit different. Why? You have delta L, you don't have upstream one. So write the downstream one, 2.17, because you are starting from here to upstream. You have YC here. You wanna see what happened when you get here. When I said what happened, it means that what's my delta X? Sorry, you have delta X, you wanna see what happened like here. Delta X1, what is Y here? Or I have delta X2, what is Y here? That's all we need to know. So I will start with the 5 meter because it says 5, 25, 100. 5 meter is here. Start writing all the stuff. We will consider that Z is horizontal. So I have nothing as a step. Area just by q over a, this one. This is easy to calculate. B plus 2y. A over this one. For SE, you have the equation, right? SF or SE, both correct. This one you cannot calculate. And this one, since it's SE multiple by or SE bar or SE average multiple by delta L, I will keep that. Total energy, I should keep that as well. Now, for the second line, I should get a number for this one. Do I have it? No, but I have delta L. So I should start guessing that. Look at here. It says that I will guess this one. So for the first one, I should say this. Less than 2.17 or more than 2.17. For sure more. Why? Because water is decreasing here. So when you start from here and go upstream, the water should increase. So your first choice should be more than 2.17. The question says that I will start with 2.35. I don't have it. I don't have it. I don't have it. So I will write this equation here. Z upstream, U upstream, V2 over 2G, the same, plus delta H. If you write it down all, you just have Y. In this one, you have Y. This one, write it based on Q over 2GB Y2. So you just have Y. This one, you have Y of downstream, you have Y of downstream. This one, again, is based on SE1 plus SE2. You have SE1. For SE2, if you write the equation, you will end up having Y of upstream in this one. So you have a long equation and it has a Y upstream inside that. Use your calculator and find the balance between these two because you should end up having the same things. E of upstream should be equal to E of downstream plus HL. That's the point of this question. Start giving different number. If you look at that, it starts from 2.35 and says that it is incorrect. Why? Because it doesn't give me the same energy for both points. For the next slide, it uses 2.25. And this time when it goes for the calculation, it seems that it will end up for this number, which is correct this time. So I can get rid of that. And this is the way that you should do that. There is no way rather than that because you need to make a balance between 2 points. This is just for 5 meter delta L. and you should do it for 25, I think. And it was 20 and 100 as well. If you do it for 120, it was 25, not 20. You will ended up this one. So you can say that at point 1, I have y for 5 meter, for 25 meter, and also for 100 meter. I was able to find my y at each point. So again, to wrap it up, we have two ways. In a first method, you have y's. You don't know what's the distance between these two. For the second method, which is a standard step method, you have delta x, you know the distance between them, but I ask you to give me the y at a specific distance. That's your job. So this is all we have. And if I have a question from the gradually varied flow, probably I will go with one of these methods. And my guess is your hardest part, let's say, is to write not writing, actually finding the balance between these 2 points, because you have a long equation and all of them is based on y. So you should put different y and make sure that you have the balance. I will post that one today for you in the Blackboard.